we started talking about feedback, and we saw that one of the basic parameters is the asymptotic transfer function, which is, and also one of the things that allows us to look at things is this asymptotic equality principle. Now, there are some general properties of feedback that we'll discuss right now, and then as we'll go, we'll see how they affect things. So one of the things that the first things to look at is what if the circuits we've looked at up until now were circuits that had no dynamics. So the question is that what happens if you have dynamics in your feedback network? So let's start with an arrangement. So let's go back to the way we drew feedback circuits. We said you had a UI plus and a UI minus, and then you have the feedback network, F, say, and then you have a UO, and this establishes your X, and this establishes your Y, the input and output to this thing. Now, if you think about this, and this was a, so this had no dynamics. So what if the system does have dynamics? What if there is some frequency dependence? And let's break it up into different pieces. We'll try to dissect it and see what each one of the parts do, and or each one of the parts does. And then what we'll see is that we'll take it from there and we just form a better understanding of the overall system. So let's just assume that now, for sake of argument, only your forward path has some dynamics, some A of S, right? Now, if you have some dynamics, some frequency dependence, if I just say, well, okay, if I just scale this up by k, the same way that we did it before, well, we'll get the same result, right? The transfer function here, the general transfer function, which is now a frequency dependent one, is A of S over 1 plus F A of S. And if I say, well, I scale it by k, then I would get 1 over F. So if your gain was large at all frequencies, then at all frequencies you will get 1 over F, or H infinity, which is great if you could do that, but it's not a particularly insightful result. We said, okay, well, we want to get as much gain as we can. But now let's assume that we have two different ranges of operation. So let's say there are some range of frequencies, probably in the lower range of frequencies, where AF, or in this case FA, or let me write it as AF, A of SF. So let's say there are frequencies where the magnitude of A of j omega F is much greater than 1. Okay? So what happens in that range of frequencies? Well, if A j omega F is much greater than 1, then obviously this term dominates in the denominator. And in that range, H of S would simply be 1 over F, as before. So if you think about it in terms of some sort of a frequency behavior, if I look at some sort of a Bode plot, log of omega, so if I'm plotting 20 log of, let's say the black is the A, so 20 log of A of j omega. Let's say A of j omega has some behavior like this versus frequency, some arbitrary behavior. Now, it says at low frequencies, and let's say 20 log of 1 over F is somewhere here, some constant. It says that at at frequencies where this difference is large, right? That needs to be the case for this to be true, right? Then your response, your H of S, H of j omega, or more actually 20 log of that, but I'm just going to draw, it's going to be like this. It's going to be essentially 1 over F. And you can see if there are fluctuations in this, if there are variations in this thing, they are just going to be all masked. They're going to all go disappear for the most part. Because you are only getting 1 over F. You don't see any of that dynamics. It's just suppressed. So you don't really care if this is particularly flat, as long as you have sufficient feedback to make this. Now, there's another region of operation. So let's just assume the opposite now. A of j omega F is much smaller than 1. So in that case, what happens? Well, in that case, this term in the denominator doesn't matter. So you just simply get what? H of S is A of S. You just see the open loop response, the forward path, just the A. So that's around here, right? So if you're much below that, you essentially see the same response as your A of S. Now, the key question is, what happens in between here? And that's where a lot of interesting dynamics can actually happen. Not that it does always happen, but it can happen. So this can look like this can look like this, it can do other interesting things, it can just blow up. All sorts of things can happen. And that's a subject of when we talk about stability and things of that sort. A lot of things that are happening in that area are of interest to us. But assuming that nothing horrible happens in this area, what you will see that when you have sufficient gain, you get 1 over f. And when you have too little gain, you just get the response. The feedback is not doing anything. And that's an important picture. Now, if you think about it, the way it looks, is it doing some magic? Because the bandwidth has increased, right? If you look at it. The bandwidth, the feedback has increased the bandwidth. So let's say, I don't know, if your 3 dB was here, so now your 3 dB is somewhere around here. Your bandwidth, the feedback has and does improve the bandwidth, but at a price. It just, the way it does it, it basically throws away, it kills all the gain in this area. Yes, it increases the bandwidth, but just like basically just by getting rid of that area, getting rid of that gain. Now, you may not need that gain, and that's perfectly fine. Then you basically use feedback to enhance your bandwidth. And I'll show you a simple example right next after this. But in general, you have to realize that the bandwidth enhancement that you get from feedback is because you're just basically reducing your gain to a level that you can sustain in a constant fashion. But it does also other things. You can see that it removes these non-idealities, these like fluctuations and variations. So let's do a quick example. So let's say your first order system, your forward system, is a first order system. So I'm A0 over 1 plus tau 1s. Or tau 1, or tau 1, yeah, let's go A1. Right? So let's say that's your gain. If that's your gain, then what happens is, so your transfer function. So let's say we apply feedback to this, and what you have, you place it in that configuration. So let's see what you got. So you will get, so h of s is going to be a1 over 1 plus tau 1s over 1 plus a1f over 1 plus tau 1s. And you get rid of that denominator. What you end up with is 1 plus a1f plus tau 1s. Right? Now, but like any other transfer function, it's most meaningful to show it as the low frequency gain times the dynamics, right? So I'm going to factor the low frequency part of this. The low frequency part of it is this thing, right? This is the low frequency part of that. So if I factor that, what do I end up with? We end up with 1 plus tau 1 over 1 plus a1f times s. So there's a new time constant, tau 1 prime, which is tau 1. So it's still a first order system, but it's tau 1, but scaled down by 1 plus a1f. Which means that my bandwidth has increased by this factor, right? Which is the same factor by which my low frequency gain, my DC gain, has reduced. You see, this is my low frequency, this was my original low frequency gain. Now it has become, it's divided by 1 plus a1f. And my time constant is also divided by that, which means that my omega h is multiplied by this factor. So what's happening here is that if you look at this picture, this plot, Originally, you had the, let's see. So the open loop system was A1 and some omega 1. But now, when you applied feedback, you got A1 scaled by 1 plus A1F, and the frequency became omega 1 times 1 plus A1F. And you can see in this example, the gain bandwidth product has remained exactly constant. So one way to do that trade-off between gain and bandwidth is feedback. You can apply feedback, you get less gain and more bandwidth. And the way you're doing it is basically by killing the gain in the lower frequencies, killing the excess gain, getting rid of the excess gain. So if you want something that runs faster but doesn't have that much gain, one way to do it is to make something that has a lot of gain and it's kind of slow and apply feedback to it and make it faster but lower gain. And that's the one of the basic premises of op-amps. You have a lot of gain, so you can trade it with other things. As long as you don't make it go crazy like this. We'll talk about that later. So is this just applicable to a like a system level perspective? No, I mean, like let's look at it from a circuit level perspective. And before I do that, actually, let me just talk about something briefly here. If you look at this picture, this calculation that we did, and if you think about A of S having something with dynamic, it's some transfer function. It basically has a numerator and a denominator, right? So if it's a lumped transfer function, it will be a polynomial. It would be a rational function of polynomials, two polynomials. So if I express it that way, let's see what we get. So if I write A of S as N of S over D of S, the numerator divided by the denominator, and I will get, and here we will get F times the numerator by the denominator of S. You should easily see that it's basically D of S plus F times N of S. So what you see here is that what has happened to the poles and zeros of the original transfer function before you applied the feedback to it. You can see that in general, the zeros have remained the same because the numerator is the same numerator as A of S, which again makes sense because zeros are the frequencies at which, complex frequencies for which an input does not produce an output. And still it shouldn't, right? But the poles have moved. So when you apply feedback, the poles start moving. And how much they move is a function of the feedback, but the location of the pole not only depends on the original poles and the feedback, but it also depends on the zeros of the original transfer function. So the zeros of the transfer function, this forward path, will have an impact on how the poles move how the poles of the closed loop system move. And this is important. So those zeros will play a role. You can't say, well, the zeros don't matter. Right? They do. Because it's the aggregate response that would determine that. Okay, so we did this like high-level kind of model. Let's do a transistor level. Let's do it at transistor level and see if there's anything fundamentally different at the transistor level. There would be a little bit more details, but at transistor level, a lot of similar things will happen. So let's construct another example, which is a variation of one of the earlier examples that we had. So it is that stage, the transimpedance amplifier stage that we had with R3 and R2, and now you can see why we call them R3 and R2, because I wanted to put the R1 here. And apply a voltage source. Remember before, what we had was a current source applied here without this one. And now we are just like replacing the voltage source in series with a resistor, and apply it like that. It's a funny looking stage. Okay. All right. So this is what we have. Again, now let's assume that we have two capacitors, C mu and C pi. You want to take these two into account. Right? So let's do it for two different scenarios. Scenario one is basically when there's no feedback, meaning R2 is infinity. Right? If R2 is infinity, we know how the circuit behaves, right? We know that, for example, what is the first order band? I mean, the bandwidth estimate of this thing. How can we estimate it? First, we have to do the zero value time constants. So you have a tau pi 0. The resistance is seen by this guy when, for example, when R2 is going to infinity first. Well, it's the basic calculation we've done before. It's the resistance with R1 in parallel with R pi. That's what C pi sees, right? So it's basically C pi times R pi parallel with R1. We've done a lot of these things before. And then tau mu 0 is R left, R right, GM R left, R right, R left plus R right plus GM R left times R right, which is basically then ends up being C mu times 1 plus GM R3 times R pi parallel R1 plus R3. So these are the time constants we knew from before. I'm just like rewriting them, and we calculated these before a couple of times. So, okay, what is the first order estimate of bandwidth in this system? If you want to look at the first order omega h in this case, we know that it's approximated as a sum of the zero value time constant, so it would be tau pi 0 plus tau mu 0. So you will get some response. Now, if R2 is not infinity, R2 finite, we can redo these calculations. And they're doable, but again, we don't actually even need to do that to see what's going to happen, and we'll see. So what's going to happen to, let's see. Well, I want to see what happens to the resistors. We want to say, so this resistor is what we call R pi 0, and this resistor is what we call R mu 0. What happens to R pi 0? Well, let's talk about R mu 0 first. That's easier. If I put an R2 resistor there, what's going to happen? It's going to be that parallel with that, right? So it's going to lower it or increase it or decrease it. It's going to decrease it. It's going to make it smaller. What is it going to do to the time constant? That time constant is going to go down. Tau mu 0 is going to go down. How about tau pi? What's going to happen to this resistor if I put a resistor here? Well, one way to think about what is this resistance, the effect of resistance at the input, is Miller multiplication, right? But remember, now Miller multiplication for an impedance, for resistance, or impedance in general, is going to divide it by 1 plus A. The reason you get multiplied by 1 plus A for a capacitor is that because the capacitor's impedance is 1 over Cs, right? Another way to see that is that if this node goes up and this node goes down a lot, you will draw more current, which makes this resistor look like a bigger or smaller resistor? A bigger resistor, a smaller resistor, right? The current is going to increase, so it looks like a smaller resistor. For the same voltage change, you're drawing more current, that's a smaller resistor. So that resistance at the input is also going to decrease. So both of these effective resistances seen are going to go down. Therefore, this bandwidth is going to definitely go up, right? As a result. Now, to see how these things happen, let's look at a numerical example. Now, and then there are two simulations, what you see. This is the Bode plot of the amplitude. The dotted one is the one for when R2 is infinity, when there's no R2. And the second one is when R2 is 5 kilo ohms. Now, in the first one, what you see is that without R2, the system has a gain of 28.6, which is like about 29 dBs, and a 3 dB bandwidth of 47 megahertz. They're all in there. Now, when you close the loop, basically when you add the R2, you will see that the gain has gone to 4. The voltage gain is 4, which is about 12 dBs, and a bandwidth of 330 megahertz. So this combination, and what the interesting thing is that if you calculate the ratio of the gains before and after, 28.6 divided by 4.03 is 7.09, 7.1-ish, right? And the ratio of bandwidth, new bandwidth to the old bandwidth, 331 megahertz to 47 megahertz, is 7.04. So you can see that the bandwidth has increased almost by the same factor, almost exactly by the same factor, that your gain was reduced. So you can see this is also true in transistor level circuits. So that trade-off, you can actually, you can use that trade-off to your advantage if you want to take advantage of that trade-off. Okay, any questions on that? Okay. So now, the next thing we should do, so I'm going to actually erase this now. So the next thing we are going to do is now, so far we looked at what happens if you have dynamics in the forward path, in the A of S. So now this time we assume the reverse. We assume that the forward path, for the frequencies at least you're interested in, has a constant gain. But now we are assuming that the feedback network has dynamics, has some frequency domain. Let's say it's a linear system, and it has the dynamics, some sort of a frequency response, so some transfer function, f of s. So you put something into here, you get a transfer function. This transfer function, of course, is from right to left, right? Because we are still assuming unilateral, and we'll come back to bilateral later. So signal's going that way. So what's going to happen? What is going to happen if your gain is large? I mean, again, we look at that general expression that we had. We did write this h of s being a over 1 plus a. Now it's basically a times f of s. And if you look at the asymptotic value of this thing, h infinity, it is simply 1 over f of s, right? Because it was 1 over f before, now it becomes 1 over f of s. So what happens? What does that mean? That your transfer function, your closed loop transfer function, well, this is really h infinity of s. What does that mean? What did feedback do? This is a lot of feedback, a lot of high quality gain applied, which you can have depending on what your dynamics, what frequency your dynamics is. If this is relatively low relative to the dynamics of this guy, this can still be, something close to this can be achieved very easily. What is this? What is this new transfer function? What has happened to the poles and zeros in this case? They have switched, right? They have swapped. Because now the transfer function of the closed loop system is 1 over the transfer function of this thing. So this is actually the inverse system. Meaning that if I take this and feed it to f of s, another f of s, I'll get x back. So I can actually invert a transfer function this way. And this is a pretty useful quality. If you have a transfer function you want to create its inverse, one of the ways to do it is using feedback. You can invert that transfer function. Now, this is what you will see, we'll see over and over and over again. So this is an interesting insight. In a properly functioning feedback loop, whatever you put in the feedback path will get inverted. We'll see more examples of that in a different domains, like different, and it happens in different domains. Well, always is a tricky word, right? So the question is that, is it always the case? Is it the case for pretty much all applications of interest? Well, it happens a lot. So let's put it this way. So as long as your feedback is sufficient. So when I say well, for a transfer function, if you have a gain for a LTI system, this is true. We'll see shortly that it's also true for nonlinearity. So if you put a nonlinearity here, that nonlinearity gets inverted. Another example of how this happens, in a PLL, for example, if you put a frequency divider in the feedback loop, you form a frequency multiplier. So when I say, I mean, it is correct in this domain, in the LTI domain. It is correct in nonlinearity. It is correct in frequency references, in phase perhaps. But if it's true in every domain of everything, I don't know. But it's true in a broad range of things. But yeah, I mean, it's true for transfer functions. So this is a very broad range. I mean, I don't want to diminish what this result means. All right? And we'll see it also it's true for nonlinearity. So, but think about it this way. If you're trying to invert something, some operation, one possibility is putting it in the feedback loop of a feedback system. So that's for that. Now, okay, so let's do an example. Let's do a circuit example of this again, just to get some insight into this thing. So here, let's say we make it, so this is an example. So let's say you have an op-amp in the inverting configuration. And an op-amp in the inverting configuration, so you have a V-in and V-out configuration here. And let's say you also put a capacitor here. I don't know, C or C2 or whatever. So we are now introducing some dynamics in the feedback path, right? So this thing, if you call this C2, you can call this Z2, right? And Z2 of S is simple to see. It's R2 over 1 plus R2 C2S. That's a parallel combination of resistor and a capacitor. Okay, so now if you have that, let's see what is let's apply the asymptotic equality principle again. So let's say this gain is very large. What does it do? It forces these two voltages to be equal. The feedback is negative. You can check. This goes up, this goes up. Well, this goes up, this goes down, pushes this down. But now asymptotic equality in this case becomes that better known the special case, virtual ground principle, right? Which basically means that this is at AC ground, and this current is also 0. AC current. So this is 0, and this voltage is 0. Both. Which means that whatever this current is, which we know because this voltage is 0, this is V in, so this current is going to be V in over R1, is going to go through here. And since this voltage is 0, this output voltage is going to be this current times this impedance with a minus sign. So V out is going to be negative I1 times Z2 of S, which is a negative V in over R1 times R2 over R1 plus, 1 plus R2, 1 plus R2 C2S. So the V out, V in, H infinity, the asymptotic transfer function is negative 1 over R1, or R2 over R1, let's write it this way, R2 over R1, 1 over 1 plus R2 C2S. So let's see what happened. So what did we have in the feedback path? If you think about the feedback network kind of looks like this, right? What is the input to the feedback network? This is the feedback network, right? If you think about this feedback network. What is the input to it? V out. What is its output? I, right? This current. And that transfer function is this. So that transfer function is the opposite, right? So if the output is I1 over V out, it's going to be the inverse of that. So it's going to be 1 plus R2 C2S over R2. So your feedback network had a 0. The transfer function of the feedback network was a 0, right? You put a 0. You have this capacitor here. Those things, you produce it, a 0. And then the feedback turned it into a pole. That 0 became a pole. And this is an example of this thing, and you can construct more complex examples of this thing if you want to. Let's do one more example of this from circuit level perspective. From a little bit more. Let me just erase this and do another circuit example. So this is another one of the circuits we had before, but now we are going to add a couple extra components to it. So we had this circuit before. I think this was R1, that was R2, but let me double check. Yeah, okay. And this was V out, so this is some V bias, some fixed voltage. This is V out, and we had a current source I in. So we had an input current source I in. It's a transimpedance amplifier. I in, and we have a voltage output. So now, let's assume let's just look at a couple of different things. So let's first, I'm just assuming that there's some capacitor here. Let's call it C in, and let's assume that there's a capacitor here C1. This capacitor is clearly in the feedback network, right? And let's look at that. I mean, just before we do any analysis, that feedback network, that capacitor in the feedback network, what is it introducing? What is it doing to the feedback network? As the frequency increases, do you get more feedback or less feedback? Less feedback, because this becomes lower impedance, right? The divider ratio becomes smaller, meaning that it's basically introducing a pole in the feedback network, right? This is your feedback network. This looks like, if I drew the feedback network slightly, well, that's part of the feedback network, but that part of the feedback network looks like this, right? It's a low pass. Right? You see it? You see it? Okay. This part is this part. Okay, fine. But let's see what this does, right? Again, going to the asymptotic equality principle, right? We can calculate what this thing looks like. So this is, by the way, this combination, we can call it Z1. Again, very similar to that. So Z1 of S is R1 divided by is R1 divided by 1 plus R1 C1S. So that's Z1 of S, because that's what the voltage divider ratio will be defined by. So how do we analyze this? Again, we go back here, we apply a K to that current source, right? So there's a K, there's a T model current source, IS here, right? There's an RM and T and IS current source. I make it K. And we've checked the sign of this feedback. It's negative already. So if K goes to infinity, to get a finite result, I know that this voltage has to be, this current, the current through RM, is going to be 0, which is the IS. So this current is 0. And this voltage is also 0, because that current is 0, and this is AC ground. So what that means is that all of this current has to go here. But now you have this extra capacitor, right? How much of the current will go through the capacitor? How much of the current? Look at the things that I've written in red and tell me how much current goes through the capacitor. 0, right? Because this voltage is 0. The voltage across the capacitor is 0. Forced by the feedback, assuming a lot of feedback, but, right? At least asymptotically, this voltage is 0, because this current was 0, this voltage is 0, so the RM sees 0 voltage across this. So if this is at 0 AC, this is 0 AC, there's no current through here. This current is 0. So, but again, what you have is that then again you have the same thing. All of this current has to go through here. So this part hasn't changed. So this was GM2, I don't know, GM1 or GM2. Call this GM1, I thought. Let me just see. Is it M1 or M2 we call it? M1, okay, GM1. GM1 V1. right? So we know that I in is GM1 V1, and now we know V1 is still related to V out through the voltage divider, except for the fact that this voltage divider now is between this impedance and this resistor. So this becomes GM1 Z1 over Z1 plus R2, Z1 of S, of course. Right? That resistor is replaced with this impedance. Other than that, everything is remaining the same. So times V out. Therefore, H infinity, asymptotic transfer function, is, which is defined as V out over I in for k going to infinity, is GM1, whatever. Now you have to kind of expand this, right? R1 over 1 plus R1 C1S divided by 1, or what's rather, R2 plus R1 over 1 plus R1 R C1S. So when you expand this, you will get GM1, you get R1 here, there you get R1 plus R2 plus R1 or R2 R1 C1S. And if you look at it from versus what you got before, which was the DC part, this was the DC part. If I factor that DC part, low frequency part, so this is H infinity of S. So H infinity of S, I'm going to factor this part. Yes?
Didn't you get everything upside down? Like, is it in 1 over this 0 over I?
Yes, I got it backwards. Yes, thank you. Okay, yeah, it's 1 over this. I got it exactly upside down. Thank you. So, okay, so it's 1 over GM1. Thank you for pointing it out. It will become R2 plus R1 plus R1 C1 S over R1. And then in the denominator, I get 1 plus R1 C1 S over R1. And then here, I get the same thing in upside down. 1 over GM, and if I factor this now, I get 1 over GM, 1 plus R2 over R1, which is what we had before, right? Then what is left would be, if you look at it, if I factor R1 plus R2 out of the numerator, I will get R1, R2 over R1 plus R2, which is the parallel combination. So just give me just give me 1 second. I may have another correction to make. Let me just write this down before I forget it. Sorry, go ahead. I flipped Z1. Yeah, I wrote it incorrectly here. I transcribed it incorrectly, but I think the calculation I did is still correct. You're right. This is R1 over 1 plus R1 C1S. And see, this is when you have a little mistake, then you make it into a bigger mistake as a result of not being careful at the next step. So yeah, but that result is correct, I think. Yes, it is. Right? Just multiply the numerator and denominator by that. So this step is correct still. And as a result, this step is correct. I just wrote it upside down here. Okay, so what did we get? So, and this I can rewrite. So now let's rewrite this whole thing slightly differently. I would write it as H infinity of S. This thing is what H infinity of 0 was before, right? When we calculated this. Times 1 plus R1 parallel R2 C1S. So what happened? You remember we said the feedback network looks like this. We drew this part of the feedback network, at least, the part that had the dynamics, R1 and C1. So if you look at this V in, V out, What is the transfer function of this thing?
One pole low pass.
Yeah, one pole low pass, and what's the low time constant, the pole's time constant? We know how to do these things now very easily, right? What's the resistance seen by capacitor? R1 parallel R2. So the time constant of that pole is R1 parallel R2 C1. So now that one pole became 1, 0 because we put this dynamics in our feedback loop. So we turned a single pole into a single 0. Got a 0 out of it. And this holds for as long as your system's gain is there. This assumes that the feedback is operating perfectly, all of this H infinity. So this result is, remember, all of these H infinities are measures of what it should be like if it was working perfectly. And then we'll see what the corrections to it are. But this is good because it allows you to design. You know what ideally it should look like, and then make corrections to it. Okay, so let's now talk a little bit more about something else. Okay. So let's talk about something that's a shorter topic. And then we'll talk about nonlinearity next time. So one of the things is that, okay, what good is feedback? Because, we said, okay, the way you're achieving something is by looking at reducing the gain where you had too much gain, for example, right? I mean, when you're looking at these transfer functions, for example, right? We said the way we are really gaining something is by just killing the gain here and making it lower. Is that all it does? Is there really so this is not a massive thing. I mean, it's a convenient thing, but what it's really doing is just lowering the gain here. Not doing anything magical. Is there something really useful in feedback? Is there something really fundamentally good about feedback? There is one thing, which is what we kind of like knew intuitively, which is that if you look at this transfer function h of s, or h, the way we wrote it as 1a over 1 plus af, the question is that how sensitive are we to different parameters? Is our sensitivity the same to a and f? Well, to get a sense of sensitivity, you can do a differentiation, for example, right? So you can calculate dh dA, and if you differentiate this with respect to the, let's see, first we're looking at the sensitivity to the gain, the forward gain. And what is the derivative of this? Of course, the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator, which is basically f. So it becomes minus af divided by the denominator squared. So you're getting this thing. And you're getting 1 over 1 plus af squared. So I want to show it in a sensitivity format. So we are going to rewrite this part, multiply and divide by a. Then you have a 1 plus af, right? So this is what you have. And now if I write it as dA over a, can I write this as dA over a? So I can take this here. I can say dH over h, because this is h, right? That is the transfer function. I can take it to the other side and bring the dA here. So I get dA over a times 1 over 1 plus af. So this is the key result, one of the key results. So it shows you what? That your sensitivity, the sensitivity of the transfer for closed loop transfer function is proportional to the sensitivity to variations in the open loop transfer function, right? But it's scaled down by a pretty large factor, 1 plus af. So it desensitizes your system to the variations of the forward loop, which is what we kind of like implied here with this picture, right? We saw that there are these variations. When you have a feedback, it becomes more flat, right? Because we have desensitized it. And the higher your loop gain is, the more you desensitize it. The higher your AF is, the more desensitization you get. And this is quite a big deal. That was actually the main reason they used negative feedback. The main reason they used that negative feedback was invented was that they were making these transatlantic lines and cross-country lines for telephone and telegraph, mostly for telephone. And the quality, because they had to have repeaters. And every time they had a repeater, there was a little bit of a distortion introduced into that. And when we talk about nonlinearity, we also see that it's more explicit. But in general, there was some distortion. So they had too many of these things, so the quality of everything was so bad, they couldn't do anything with it. And they said, okay, you know what? If we have a lot of gain, the gain is not a problem now. We have better devices, we can make more better gain, so we can trade some of that with desensitization, make a better, more, have a higher fidelity response, and trade it with the gain. So that's a good thing. Right? Now, how about its sensitivity to the F, to the feedback itself? Right? So we can do a similar analysis. Now we can do DHDF. Right? And DHDF, the numerator is 0, the derivative of the numerator is 0, so we get only the negative of the derivative of the denominator, which is negative A divided by 1 plus AF squared. And if you look at this, you will recognize H right there. You get negative A over 1 plus AF times 1 over 1 plus AF. Right? So so this is H. So we can move it to the other side. You get DH over H is negative, and then you get DF. So I'm dividing and multiplying by F. Yes, it should be A squared because it's the derivative of the denominator times the numerator. Thank you. So there's an A left here, and that makes a lot more sense, actually, if you look at it this way. So look at this now. The sensitivity in the H, this H is almost as sensitive to F, right? So variations in F result in similar variations in H, because if AF is large, this ratio is almost 1. So whatever sensitivity, if you have variations in your feedback network, it would directly reflect itself in the transfer function. So that's why, in general, when you design a feedback network, you want it to be designed in terms of parameters that you can control well. You want it to be defined as ratio of two simple resistors that you place close to each other so they're at the same or similar temperatures. Or you kind of interleave different pieces of them to be even like more closely related to each other. If it's on chip, you want to make sure that they don't have the least amount of process variation. So you take one finger of this, part of this resistor is here, the part of the other resistor is here, the part of one, and then you interleave them so the variations kind of average out. We talked about other techniques like common centroid and all those things. And depending on how accurately you need something to be, how repeatable it may need to be, you need to be careful because there is no desensitization to feedback variations in the feedback network. There is desensitization to the forward path, but there is none for the feedback path. And that's an important thing because it allows you to design in such a way that is conducive to repeatability and reliability. Okay, so any questions on that? All right.